Now I'd like to introduce Mark Musin, who will be speaking about metadata and the CBK lifecycle. Mark is professor of biomedical informatics and data science at Stanford University, where he's director of the Stanford Center for Biomedical Informatics Research. He conducts research related to open science, intelligent systems, computational ontologies, and biomedical decision support. His group developed Protégé, the world's most widely used technology for building and managing terminologies and ontologies. He served as principal investigator for the National Center for Biomedical Ontology, one of the original national centers for biomedical computing, and he directs now the Center for Expanded Data Annotation and Retrieval, acronym CEDAR, founded under the NIH Big Data to Knowledge Initiative. Mark, we're really grateful for you to be here and are looking forward to your presentation.
Thanks so much, Chuck, and it's really exciting to be here as well. Though I have to confess, I got the feeling I was drawing the short straw. People got to talk about exciting applications of MCBK. People talked about how this trend is taking over the world. You asked me to talk about metadata. For many people, metadata is kind of boring. I think metadata is exciting, but I want to try to give you the next half hour or so a feeling for why I get excited about metadata and actually why it's so important for the work that we're doing. And in fact, I have to confess, yesterday, the word metadata appeared many times in our conversation. And I guess within this community, at least, people understand what the librarians say when they say that metadata is a love note to the future. In our case, we actually have a lot to say about metadata, and metadata has a lot to say about the computable knowledge that we want to implement. And what I want to do in the next few minutes is to give you an overview, not only about where I think metadata needs to play a role in MCBK, but also to emphasize that there's been an enormous amount of work dealing with not just computable knowledge, but just software in general over the past few decades. And I think it'd be helpful if we could actually place our work in the context of what others have been trying to do to be able to make software modules more expressible, more reusable, more understandable. So it all kind of fits together. And before I do that, I want to emphasize that metadata is not just a love note to the future. We need it in the present. And perhaps one of my favorite stories is the story of the Mars Climate Orbiter that some of you may remember from about 20 years ago. Mars Climate Orbiter actually never orbited Mars, because as it was injected into Mars orbit, there was a small problem in that the information coming from Lockheed Martin on the ground misunderstood the metadata that was to be received with the data that was going to the actual orbiter. And I guess the Lockheed Martin data were in foot-pounds, and the orbiter was expecting newtons. And because of a metadata problem, we lost the whole thing. Whether it actually crashed into Mars or whether it's orbiting around the sun, we don't really know at this point. But metadata really matters a lot, and it really matters a lot to us. When people think about it, how do we then deal with the mechanism by which we want to talk about software, and how can we describe software in a way where we can reuse and find the appropriate software modules we're interested in? I have to think back to the 1960s. Many of us, if you scratch enough, will remember how we used to have whole libraries of subroutines that we embedded within our code. And IMSL subroutine libraries are probably the canonical example of that. But there are whole kinds of volumes of software that we purchase that come with libraries that allow us to do the kinds of things we want to do. Now, whether a software library that includes a regression program or a fast Fourier transform or something like that is necessarily computable knowledge, hard to say, but all of these software libraries are always associated with books that tell us how to find the right routine that we want to be able to perhaps use our understanding of the problem informally to search a book informally to find the right subroutine that we might want to embed within our code. And that's why we did it for decades. And that's really just vanilla software. It really wasn't until the 70s that we started to recognize that we needed to talk about actual software that imbued knowledge. This is a picture of a cover of a publication from an NIH agency, which doesn't exist anymore, the Division of Research Resources, which was responsible for funding much of the early work in AI and medicine, and really emphasizing the importance that computable knowledge played all the way back 40, 50 years ago. I'm often asked what is depicted in this publication. It appears to be a doctor, and I assume that's a doctor because it's a white male with a stethoscope in his ears, and I say that facetiously, whose neurons seem to be directly connected to integrated circuits which go to a mag tape drive. I don't understand the computational architecture here. I think I need someone who actually has more experience to explain this to me, but you can get the sense that certainly in the 70s, we started to talk a lot about biomedical knowledge. We talked a lot about putting biomedical knowledge into computers, but it was still an era of mainframes. It was still an era where we really didn't have the internet for many interesting things at that time. And we weren't able to effectively say that we had anything that was computable, or certainly anything that had metadata. Now, by the time the 90s came around, the AI community was certainly moving beyond the kinds of large mainframe applications that permeated previous work. And there was a lot of discussion at that time, which I think a lot of us have forgotten about the idea of reusable problem solvers. This work has been supplanted by a lot of things that have come subsequently, but I think it's really fundamental to the kind of work we want to do now in MCBK. In the 1990s, people recognized that we could create problem solvers that were independent modules that could work in a way where they could perform recurring tasks like classification, fault diagnosis, planning, constraint satisfaction. And the idea would be that these problem solvers would be linked to knowledge bases that would contain all the domain-specific information about the area of interest that you had. And developers could mix and match a problem solver, say, for classification with a domain, say, about internal medicine, and suddenly you had a problem-solving system that could do diagnosis in internal medicine. This became a really major area of interest, and in the 90s, there were hundreds of people looking at this kind of stuff. It was really attractive because you could take this constraint satisfaction problem solver and you could add constraints about circuit board layout, and you suddenly had an intelligent system that could do layout for a circuit board. You could add constraints about how to do scheduling of events, and suddenly you had a problem solver that could do scheduling. Add constraints about drug-drug interactions and drug effects, and suddenly you had a constraint satisfaction problem solver that could help you select the drugs that you wanted to add together to create some cocktail to address some problem, like giving multi-drug therapy for HIV. Alternatively, you could start out with a knowledge base, like a knowledge base of diseases and manifestations. You could say, well, let's add a Bayesian inference problem solver and solve the problem of medical diagnosis using a Bayesian approach. Let's add a problem solver that uses a planning method like internist one. Let's use causal reasoning. And you could basically do this mix and match. And it turned out to be a really big deal. A company called Trilogy, for example, which is one of my favorite companies because, like many others, it was a spinoff of Stanford, created by students who dropped out and found they had something better to do than go to college, I guess. What Trilogy did was build a really great constraint satisfaction problem solver. And they discovered that they can go into a customer site. They can elicit domain-specific constraints for whatever the task is that the customer needed. And this is a company that really made a ton of money by having a constraint satisfaction problem solver that was reused over and over again with new knowledge bases that brought in new information about new domains. So the challenge in this kind of an approach is that given a task, like putting together a circuit board or scheduling some device, there may be more than one problem solver that's appropriate. If you think about something really trivial, like how do you multiply two numbers? You can use multiplication tables, you can perform repeated addition, you can add logs. How do you know what is the right one to use? And the answer is, well, you need to have a mechanism. You need metadata to describe what the problem solver does so you can pick it out of a library. And so around this time in the 1990s, people got really excited about something called the Universal Problem Solving Method Language, or UPML. UPML is probably the most important piece of problem solving metadata that you never heard of. It was intended to support all kinds of things like searching for appropriate problem solvers in a library, reasoning about what a problem solver does, integrating a problem solver with domain knowledge at design time by knowing how to basically link up the problem solver with the kinds of data and knowledge that it operates on, integrating problem solvers and domain knowledge bases at runtime so that as a knowledge base evolved, you would know how the new knowledge might relate to the problem solver that would operate on it. The result was pretty arcane. And basically, the best that ever came out of UPML, I would say humbly, was this system, which we developed at Stanford with a really arcane version of Protege, one that has not been around in about 20 years, which shows you the kinds of things that UPML cared about. It would have preconditions that would enumerate when could you use this particular problem solver. It would have information about what was the world like before the problem solver operated. And it would have post conditions. After you ran this piece of problem solving machinery, what was the condition of the world? What did the problem solver basically do? What are the problem solver subtasks? How do we piece it together with other problem solvers? And frankly, this was just really hard for people to understand. It was, I think, a really exciting piece of work to which hundreds of people contributed, but it really didn't get us very far. In the 2000s, we said, okay, well, let's move on. Let's think about other ways in which we can perform problem-solving behavior, perhaps not with such complexity, perhaps not without the flexibility of mixing and matching domain knowledge bases and problem-solving methods. Let's think about web services, because by the 2000s, the web was everywhere. Web services were everywhere. And the semantic web community said, look, we need a mechanism whereby we can use web services to automate problem solving to give us a kind of intelligent agents that the web demands. And so when the semantic web community first was formed, the emphasis really was not on linked data, as is the case now, but really the emphasis on how can we build intelligent agents that operate on the web, that use web information in machine processable form in order to perform important activities that typical consumers would want to have. And out came WSDL or WSDL, the Web Services Description Language, which was an XML mechanism for creating metadata to describe what web services would do. And people said, okay, we don't need UPML. We have WSDL, and WSDL became the basis, at least for a while, where there was a lot of excitement about creating online computational agents that would perform intelligent things. Lots of enthusiasm. And then for reasons that are probably more a function of how complicated WSDL is, and frankly, how hard it is to edit very large descriptions in XML, WSDL kind of went away. It's still used, obviously, it still has importance, but it led Jim Hendler, when he was editor of IEEE Intelligent Systems, to pose in an editorial, where are all the intelligent agents? And fundamentally, what Jim was pointing out is that the idea of computable knowledge distributed on the web was sort of being supplanted by all the enthusiasm at the time for linked data, and the agents were going away. And frankly, we could not really turn to the semantic web community as we had thought as the basis for a lot of work on the idea of computable knowledge. And in fact, I think that's why MCBK has really had a mandate because the idea of intelligent agents on the web, while important, has not had the same kind of groundswell of support that it used to have. And I think the MCBK community recognizes why in biomedicine this work is important. And so now it's the 2020s. And as we talked a little bit yesterday, the MCBK Standards Working Group has proposed a set of CBK metadata categories, like type and domain and purpose and ID and location and so on. And these categories are not actual metadata descriptors, but they represent a really important start to the kinds of things that we want to say about intelligent problem solvers so that we can begin to talk about what the problem solvers are. Fundamentally, as we've heard over and over again, if we want to make problem solvers fair, we want to make our knowledge fair, these are the kinds of things we have to say about them. And as I'll say in a moment, then now the challenge is figuring out what we actually need to say within these categories. So the story so far is basically that we've been struggling to develop metadata for computable knowledge for a really long time. And I would argue it started in the 1960s when people started to figure out how to describe mathematical subroutines in books. We've seen UPML, we've seen WSDL, we've seen the beginning of metadata as MCBK is beginning to define it. We're working really hard. We haven't gotten it right yet. And I would argue we keep screwing up because we're overly ambitious, because we look at things like UPML that really try to say too much. UPML in particular tries to say things that are really abstract. And we keep working in XML, which really doesn't give us very good authoring tools. The Cedar Workbench, which Chuck mentioned, is something my team has been working on for a long time, which allows us to encode metadata for different classes of digital objects, and it allows us to be able to fill in templates with appropriate terms to create standardized metadata. So if we think about metadata as a set of attribute value pairs, we can look at these attributes, we can fill in them with values, and most important, we can fill in those values with terms that come from standardized ontologies. And I've been working over the past few months with Alan Flynn, thinking about how we might apply this kind of technology to the metadata that we need for MCBK. That work has been stalled, but we really want to move forward on it because I think it's really important. And as I said, we need this metadata because we want to make our computable knowledge fair. We're in the situation now where everybody and his brother is talking about fair data. We've been talking about it in this meeting, and everybody talks about fair data. It's really hard to make metadata fair, because if you look at the founding principles for fair data, if you look really carefully, and we're not going to go through all the details here, it's really amazing. Most of those principles deal with metadata. And I would argue that what makes data sets fair is the metadata that are used to describe those data sets. In fact, that's why CEDAR is so important in the open science community, because it provides the basis for creating metadata to describe data sets that are based on standard templates and standard ontologies. Well, the same thing is important for software and for CBK. And I think what's really timely is that just last month, the FAIR Principles for Research Software Research Group, working group rather, released proposed standards for fair for fair software. And so the FAIR for RS working group, which is convened by the Research Data Alliance, Force 11, and the Research Software Alliance, got together and said, look, if we want to make research software fair, as we would want to make CBK fair, these are the kinds of things we need to be thinking about. If we want to make our software findable, then here are the things that we need to include. And you'll note that software to be findable needs to have rich metadata. It has to have metadata that clearly and explicitly include the identifier of the software that they describe. Then the metadata are fair and searchable and indexable themselves. If we want to make software accessible, then we need metadata that are accessible, even when the software is no longer available. If we want to make our software interoperable, then we need to have metadata, qualified references to all the objects that the software references. If we want to make our software, and by extension, a CBK reusable, then we need to have software that is described with a plurality of accurate and relevant attributes. We need detailed provenance information for our software, which is another element of the metadata that we would be using. And our software needs to include qualified references to other software. So just as when we think about making data sets fair, the emphasis is on the metadata. It turns out the FAIR for RS working group also said research software is no different. That our research software, if we're going to make research software fair, needs to have principles for software that align with the principles for data in terms of fairness. That means making software fair depends on the availability of good metadata. And because CBK is software, I think the standards that are being recommended by the FAIR for RS working group are really important for our community to pay attention to. Not that they are directly related to all the things that are necessary for fair knowledge, and not that they address all the categories that the MCBK standards group has identified, but they really form a good start. So if we take a step back, think about where we've come since the 1960s. We haven't solved the problem of metadata for CBK by any means. In some sense, I feel like I was set up. I haven't told you how to make all of our make our online knowledge trustworthy, trustable, and fair. But we do have the beginnings of how to make the metadata for such knowledge better. Getting metadata right for software is really hard. Getting metadata right for computable knowledge is going to be even harder. And I think the metadata categories assigned by the MCBK standards working group really give us a good framework for getting going. But those are just categories. And I think the hard work is going to be in taking those categories and coming up with standard descriptors for the metadata that we need within each category so that we can create metadata descriptors for online biomedical knowledge that really allow us to make those data sets and make the software pieces fair. So basically, the FAIR principles for research software certainly give CBK metadata something to which we should aspire, but they don't fill in all the blanks. And there's really a lot of hard work down the road that we need to be able to take recommendations such as these, to take the principles that are associated with fairness in general, to look at what has been done in the past in terms of, say, UPML and WSDL, to look back at what we used to do just simply in natural language dealing with software subroutines, and use that to inspire us. Because frankly, fairness is really important. Certainly the developers of online data sets understand why fair is key. And I think as we think more and more about online computable biomedical knowledge, we have to make those knowledge modules fair. And to do so, we have to build on the past, but also we have a lot of hard work going forward. When we stop that, I'm happy to open things up to any questions that you might have.
Thank you, Mark. Truly excellent presentation. I'm delighted with all the insights that you've provided for us, and I have to tell you that I had a light bulb illumination moment as you were talking, and I'm going to take the prerogative of the podium to ask you the first question based on my light bulb. It illuminated when you were showing all of the furor around fair data. And that led me to wonder whether metadata about knowledge is in and of itself a confusing term, because it's like an off-diagonal matrix element. Metadata is data about data. Meta-knowledge would be knowledge about knowledge. But we're off the diagonal here and maybe not using the prefix meta appropriately, because we're talking about data about knowledge. Do you think we need a different term, or do you think everybody just kind of knows what we mean and this is causing no confusion whatsoever?
Chuck, you are always the philosopher. I don't think there's as much confusion about that because, frankly, when we talk about meta-knowledge, we're usually talking about a meta-concept that is extremely abstract about something which is also abstract. And I think one of my biases, and this is actually a bias which I should have made more explicit, is that in our conversations about CBK, we're really talking about software artifacts. We're not talking about knowledge as it exists in our head, or as George Strong would say, how we might use it to accomplish things in the world. We're using it as a way for talking about how pieces of software can be taken out of a library and put to use for a particular purpose. And so we're not necessarily talking about metadata. We're not talking about meta-knowledge either. We're talking about meta-artifacts, if you will. We're talking about ways of describing what's in our library. And frankly, since we use the word metadata so conversationally to talk about whatever we might put in a library, whether it's a library of books or a library of software or a library of whatever, I think metadata is fine for our purposes. We just have to be very clear that we're not talking about knowledge in the philosophical sense. We're talking about knowledge as an artifact that we want to be able to access for the purposes of building some system that's going to do something useful in the context of, say, a learning health system.
Okay, thanks, Mark. You've settled my light bulb down greatly. Thanks very much. Guns Koru posted a comment that we'd like you to respond to. The software maintenance field looked into these problems, but with the agile movement, software documentation was not focused on. Business pressure and the need to put products out there was overwhelming, so software documentation was often put aside. How does your own thinking resonate with that?
I think the point is well taken. I still think the results of agile development require some documentation at some point, but I think our whole community is more than just a community of software builders. I think we want to be able to create reference implementations that can be taken out of libraries and put to use. And I think as soon as we're building libraries rather than just pieces of software, we have to find them, we have to access them. All the FAIR principles come to play. So I think in that way, fairness is important and metadata are important. Maybe not metadata to the extent that would allow us to document the complete innards of a piece of software. But frankly, we need enough metadata so we can trust the software that we do take out of libraries.
Okay, thank you. I'll move to a question from Bob Greenis now. Getting at the wisdom question, we can't seem to get away from wisdom today, and the universal problem solver over-ambitiousness. How much effort should be expended to encode in metadata the how and when to use a particular knowledge resource? It strikes me that the encoding is sufficiently difficult that people wouldn't do it.
I think that's really hard. And I think we should never be putting into metadata things that we don't have a vocabulary for discussing in natural language. And I think that was a fundamental problem with UPML, that if we don't have a way of talking among ourselves about what knowledge might be good for, we certainly can't encode it as metadata. On the other hand, we're very good in doing things that provide examples. So even though we may have difficulty describing in an intentional way what knowledge exists in some artifact, we can be really clever in showing how that artifact gets used in a variety of applications. And I think we've already had some conversation about that at this meeting. So I think metadata that provides examples of where a piece of knowledge has been useful are going to be very important for our work. Because even if we can't describe in abstract terms when a piece of knowledge is useful, we can certainly say that's where it's been valuable.
Okay, thank you. This goes a little bit to our governance discussion earlier this morning. Who do you think should define metadata standards for CBK?
That is a great question, because we don't really have a standards organization that is appropriate. I think actually if we were to create a membership community, that would be a really important driving function, because I don't see an existing standards body that is in a good position to do that. I think over the years, there have been groups that have been self-appointed that have tried to deal with representation by medical knowledge. None of them has been successful. And part of the challenge has always been those groups have always been questioned because of potential competing interests. So many years ago, a group of representatives of pharmaceutical companies tried to create libraries of online biomedical knowledge resources, and the idea that pharma was involved made those knowledge resources suddenly untrustable to almost everybody else in the healthcare community. HL7 certainly is very involved in standards, but of course they're heavily influenced by vendors who have a profit motive. I think, as I think about it, there really isn't an obvious place that comes to my mind right now, and that might be another reason for creating an MCBK membership organization.
Okay, thank you. We'll give Blackford Middleton the last comment. I worry also about the interaction of humans with cognitive support systems /AI. We will definitely need guardrails, perhaps, to define both appropriate users, such as humans, and the appropriate AI. Thoughts?
Yes, I agree, Blackford. And I think our greatest challenge is understanding what are the limitations of systems that we build, understanding what are the biases that were in the data from which those systems may have learned. I think that's an incredibly important area. That's why explainable AI has gotten so much buzz. But clearly we know of lots of examples where systems that have done machine learning from large databases have really replicated biases in those databases in very dangerous ways. And I think, frankly, one of the major roles of metadata is going to be able to provide the provenance of those kinds of systems, allow us to understand what biases might have been cooked into the corresponding AI systems, and the ability of humans to be able to intercede and know when things are going to be most appropriate and most wisely used.
Okay, thank you. Again, Mark, this was a superb presentation, and we benefited from your insightful responses to our questions and comments. We very much will appreciate your help going forward as MCBK continues to evolve. Thanks again for your presentation.
Thanks, Chuck. I enjoyed it.